To begin describing our project, we will first start with the dataset. The dataset is simply an undirected graph. It says directed graph in the title, but on Stanford Snap, it is an undirected graph. And the only reason it's saying directed graph is because if there's like, for example, a edge from 0 to 1, it's also there's also an edge from 1 to 0 because an undirected graph is just a directed graph with edges that are double facing. So this is the initial text file we decided to use. We checked on Discord, and to process a file like this with all our pathfinding algorithms and our DFS traversal would take, as we tested, 5 to 10 minutes, just because there are 500,000 lines in this file. So in order to circumvent that and still test our functionality, what we did was we created smaller tidbits using the exact same format, which we can test. These are around 130 lines, and basically just give us different inputs and edge cases that we were able to configure our project upon. And there's specialized test cases too for some of the algorithms we use that we'll get into later. So to start off, we have to obviously load in the file, and that's where we use our undirected graph class. It's a pretty simple implementation. All we're doing is we're taking the file name, we're loading it into our graph, and the graph representation that we decided to use was an adjacency set. So this is just a spin-off on an adjacency list, which is basically a vector of linked lists, with each index of the outer vector being one of the nodes, and in the inner vector, each array is just all the vertices or nodes that they're adjacent to. A linked list would kind of mess up our time complexity in certain scenarios, so we decided to use a vector of sets, and it achieves the same thing because an item must be unique in a set. So now that we've gone through that, we can go through some of our pathfinding algorithms. So a general overview, we can't get into everything, but shortest path is using a modified BFS with a visited vector so that we're not visiting nodes again. And essentially what it's doing is it's spreading out in all directions until it reaches this connection if whichever node is there is equal to the end node. And then it breaks because we know we found that end node, and we've expanded in the least distance from the initial node. So this is really just a helper function. This isn't what one of the criteria of our projects, but it goes really nicely with one of the uncovered options, landmark path, because landmark path, what we discovered pretty early on was that landmark path was just shortest path twice. Shortest path to the landmark you're trying to visit, and then shortest path to the end. And we had handled some additional edge cases here. This is just a standard DFS traversal, just traversing purely through depth. Other than handling an edge case, if the node was even in the file and if it was in the bounds, it is pretty straightforward, and it uses this helper function where it recurses. And next we have another uncovered option, which was connected component and strongest connected component. So connected component really is just a helper function. All it's doing is it's gathering like a component, which means that every node in that component can visit another node. So what it's doing is it's gathering the largest sized component, and that is actually very helpful, because the whole idea of a strongest connected component is if you have an entire graph, right, an entire dataset txt file where all of the nodes can achieve a path from one to the other. So this is just using connected component and checking if the size is equal to the actual amount of vertices in the entire graph. Now, since we've covered that, I'm going to go over some of our test files. So we're just checking for basic functionality and some edge cases, right? If the DFS, like the node that we're traversing, starting from, even exists in that file. What happens if the node is not found, like I mentioned earlier, or if the node is out of bounds. And then we have landmark path. We're just testing on some inputs and verifying that with our knowledge of the data sets. And again, testing for some of the similar edge cases that we saw in DFS. But with that added complexity of that, we're not only going to another node, we're going to another landmark node, right? And then we're going to the destination mode. So we're also making sure that's covered. and then strongest connected component. So here we actually had to design two test cases because the original test cases were just snippets of the 500,000 line data set test case. So here we actually had to design a strongest connected component where a path is achievable from each node to the next, just because the entire graph or even snippets of that entire graph would not achieve that. And we're also testing that if there is no connected component, that it returns an empty vector, and similar edge cases like that. Here we have our shortest path. This is really just the helper function we used for landmark path. And so this is basically just an additional level of thoroughness covering landmark path. And then we have undirected graph. We're just testing if it can be loaded in, if it's gathering the right amount of inputs. Our add edge functionality, which was critical to our graph representation with an adjacency set, and just edge cases and things like that. So now that I've shown how everything works, I'm just going to run the tests just to make sure that all of them run and to show you guys that. So first for DFS, I already made all these, so I just can write the run commands. So for DFS, that's just /DFS test. DFS is running, and then landmark path /landmark path. /landmark path test. And for strongest connected component, it's just /scc test. And then for shortest path test, which was our helper function, it's just /shortest path test. And then for our last test, it was just testing the basic functionality of the graph and its ability to load in data sets. It's just /undirected graph test. So this is all our functionality working and everything we achieved here in the project. We were able to finish and test all of our algorithms, and this is the completed project.